In this video, I will show you what the DQ coordinates are and how you can use a controller in DQ coordinates to control a three-phase inverter. In order to understand what a DQ frame is, you first have to look at how you can reduce from 3 phases into 2 phases. So if you look at a 3-phase system, we have phase A, phase B, and phase C. And if you sum up all of the phases, phase B plus phase C, you will always get 0 for a perfectly balanced system. So this means that if you only know phase A and phase B, you must know phase C as well. So this means that we can represent this 3-phase system with only 2 phases. The last one is redundant. And we can do this in alpha-beta coordinates. That is what is most common to do. And the transformation from ABC coordinates to alpha-beta coordinates is called a Clark transformation. So if you want to look more deeply into that, you can search up Clark transformation on the internet. So this is what it looks like in a phasor diagram. And these are the equations to transform between ABC coordinates and alpha-beta coordinates. So the reason why there's a gamma here is just in case the system is not in balance. So you can see when it is in balance, when A plus B plus C equals 0, gamma always becomes 0. So if you look at, this block here converts from ABC coordinates to alpha-beta 0 coordinates. So if you look at that, I think they came on top of each other. You can see that this is alpha-beta coordinates and this is ABC coordinates. So you can see that alpha is exactly equal to the phase A, and the beta is 90 degrees shifted from phase alpha. So yeah, it looks basically like that, and the orange one is the gamma. Now, for the PI controller, the best thing would be if the coordinate system was constant, or if the values were constant that we wanted to control. And you see that this is not the case because the current reference is sinusoidal. So the PI controller has to make a sinusoidal current. So it has to follow this sinusoidal reference, which it's not very good at. It would have been a lot better if this sinusoidal current was constant. And now we can use a DQ coordinate for this. So a DQ coordinate is basically the alpha-beta coordinate, but just with a rotating speed. So it's rotating with an angular velocity of omega. And you can see that the angle between D and alpha is theta here. Now, if we calculate, we can actually calculate theta analytically. This is not how you would do it in a controller, but it's great to understand how it works. So you can do some math, and then you will get theta. And this is the angle of the beta coordinates. So if you look at this, you can see that if you multiply this theta value, not multiply, but if you take the sine of this theta value and scale it, you will get the beta coordinates, the beta signal. So you can see that the beta signal is sinusoidal. And this means that the alpha signal is cosine. So if we go back here, you can see that this is the equation to calculate the DQ coordinates. So you have a alpha coordinate, which is cosine of theta, multiplied with the magnitude of the voltage. So we have V alpha, the magnitude of it, multiplied by cosine. This is V alpha. And you multiply with cosine, so you get cosine squared. And you can do the same for the beta. You multiply, so we have the magnitude of the beta, and then you multiply it with the sine of theta, and then you multiply with the sine of theta again. So you get it squared. So if alpha and beta has the same magnitude, this becomes 1. So then it's constant. And if you do the same for VQ, you will also get that it's constant when the magnitudes are the same. So this means that by using DQ coordinates, we can actually transform from ABC coordinates into a stationary frame, which is DQ coordinates. So keep in mind that there are settings inside this block, which transforms from ABC coordinates to DQ coordinates. So I've chosen align with phase A axis. And we can do the same for the reference current and the actual current as well. So you can see that all of them are sinusoidal. This just has some ripple. That is why it also has ripples in the DQ coordinate system. So you can see that if we implement the DQ coordinates into the current controller, it becomes very similar. You can see that we have still the reference minus the actual current, and then we feed that into a PI controller, and then we add it with the DQ coordinates of the grid voltage. And then we get VM, which is the voltage at this point here for each phase. And then to get the duty cycle, we divide by the DC voltage, DC link voltage, to get the duty cycle, and we transform the duty cycle back into ABC coordinates. And this controller works well, so we get about, we can control the current to about the reference current with some ripple, and you can see that there's a little bit of a offset here. That is just because I haven't tuned the controller properly. I just set some random values. So if you're not familiar with this type of a PI controller, I use this type of PI controller, while this is the standard one. So there's one last thing, and that is this feed forward is actually not ideal. When you transform from ABC coordinates to DQ coordinates, there is something else that also adds in, but I will not explain it in this video. That will be a later video. So if we now look at how the current what the current looks like, you can see that it becomes sinusoidal after you've transformed the duty cycle and fed that into the PWM and then into the MOSFETs. So that's basically how the DQ frame works. And if you want to try this Simulink model, you can just go into the description below.